to the Journey Shake Chem. Well, today's warm-up is just a little bit of review. It's going to be old stuff for you. You're going to know it, no problem. Well, please do the best you can, and we'll discuss it in a moment. Number 1 asks for us to list and describe the 3 categories of electrolytes. Well, first we have acids, which we are revisiting today. And the acids, we know they're acids because they begin with hydrogen, except for water. The second category would be bases, and bases are metals with hydroxide. Therefore, methanol, CH3OH, is not a base. That OH is an alcohol group, not a base, not an hydroxide. The third category are the salts, the metals with the nonmetals and the metals with the polyatomic ions. And those are the 3 categories of electrolytes. Then we are asked to list the 7 strong acids. It's very, very important that we know these 7 strong acids. And they are hydrochloric acid, hydroiodic acid, hydrobromic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. Those are my 7 strong acids, and it's going to be very important for us to distinguish the strong acids from the weak acids. Today we're going to start the final topic. I know you're as excited as I am, and we're going to revisit the penguin. So I'll be right back. Up until this point, we have said that water is a non-electrolyte. And basically, it does not want to dissociate. However, we have what is called the ionization constant for water, and it is the symbol that we use for it is a big K for the constant of water. We have the W, and that value is always 1.00 times 10 to the negative 14th. And that means that water will dissociate somewhat into its parts, and here we have water that breaks up into its hydrogen ions and its hydroxide ions, or we could break it into hydronium ions and hydroxide ions. We use hydrogen and hydronium interchangeably. So oftentimes when I ask for the hydronium ion, I'm just getting you used to another form of hydrogen, but they are the same, very same things. And what I want you to do is have your calculator, and in your calculator, I want you to put in the number 1 exponent minus or negative 14. Then press the log button. When you do that, you get negative 14. And that leads me into the pH scale. On the pH scale, it goes from 0 to 14, and 7 is neutral, and 0 to 7 is acidic, and 7 to 14 is basic. When we have more hydroxides than hydrogens, then the solution is basic. If we have more hydroniums or hydrogen ions than hydroxide, then the solution is acidic. Acidic things are like fruit juices, orange juice, lemon juice, vinegar. Those are some of our acids. Hydrochloric acid is in your stomach, and it's way down here. Basic things are things like milk and soap and Tums and antacids that we use to settle down those acids sometimes in our stomach. Well, we have this scale, and we use this scale as a very simplified way of looking at acids and bases. Now, the way that I'm going to use this on the very first worksheet is that I know that when we write an equilibrium expression, or using this equilibrium constant, for the first equation that I had, I get my hydrogen ions and my hydroxide ions. And my K value is my products divided by my reactant. This is my Kw. It's very important to note here that we do not include pure liquids or pure solids. Therefore, Kw equals the concentration, and these brackets mean molarity, of the hydrogen ion times the hydroxide ion. And therefore, when we look at this, I have the hydrogen ions, or the hydronium ions, times the hydroxide ions. Now, if this is C, it equals A times B. If I am given two of these values, and Kw is always 1 times 10 to the negative 14th, then C divided by A is equal to B. And C divided by B is equal to A. And therefore, if I'm given one of these values, I can determine what the other concentration is. Now, it's very important to understand that these concentrations are exponential numbers. And we'll discuss a little bit later how we get from the exponential number to the whole number or the rational number. But this will help you on the first side of the worksheet. You have two of these things and you are determining the other. I know you can do that, and I'm going to be right back to discuss the other side of the worksheet. Here we have an expression of how we determine pH. And pH is negative the log of the hydrogen ion or the hydronium ion concentration in molarity. And pOH is minus the log of the hydroxide ion concentration in molarity. And the pH plus the pOH is equal to 14. And you'll recall that when we took the log of 1 times 10 to the negative 14, we got 14. And when we're multiplying, we originally had that the Kw was equal to the hydrogen times the hydroxide. Well, when we are multiplying an exponential number and we switch it to a log, then we are adding those log numbers. And therefore, the pH plus the pOH is equal to that 14 because we're taking it out of the exponential form. And notice that when we did this, we got a negative 14, and that's why this equation here has a negative sign, so that our values always come out to be positive. And these are very, very important relationships that we need to refer to as we go. I'm going to work number 1 and 2 on the second side of this worksheet with you. Well, we are given a pH of 2.55. So we're given that the pH equals 2.55. And I'm looking for the hydrogen ion concentration. So I am going backwards. I'm not taking the log of this number. I'm undoing the log. And therefore, if you notice on your calculator, it says log here, and above it, it says 10 to the x. And 10 to the x is the opposite of the log. And therefore, that's the ones that we need to use. I put this number in my calculator, 2.55. I make it negative. And then I take the inverse log or I shift log. And when I do that, I get 2.81 and 83 times 10 to the negative 3. And we're always going to take these numbers to the hundredths place. So therefore, my answer in this case is 2.82 times 10 to the negative 3 molar hydrogen or hydronium ions would be the answer to my first question. We're going to round them always to the hundredths place. Both pH and the concentrations we will take to the hundredths place so that we're doing these things consistently. Now, it is more difficult, or it takes another step to go from pOH. If I'm given a pOH, let's do number 2 together. The pOH is 4.55. Therefore, I'm going to subtract it from 14 to get the pH. And therefore, in this case, the pH is 9.45. Then I follow the same format. I make the number negative, and then I take the inverse log or shift log to get to that 10 to the x. And my number is 3.5481 times 10 to the negative 10. And you'll notice that this exponent is one less of my pH number. That's a relationship here. And my final answer then is 3.55 times 10 to the negative 10 molarity of the hydrogen ion. And you'll recall that the hydrogen ions and hydronium are interchangeable, and that would be my second answer. It's very, very important to make the number negative. Otherwise, you come out with a very large number rather than a very small number. And when our Kw is equal to 1 times 10 to the negative 14th, this negative 14th is a tiny, tiny, tiny number. That means it does not dissociate very much on its own. Its auto-ionization is very, very small. And that's why when we're working all of these problems, we will have a negative exponent, which shows us that it's mostly reactant and not very much product. Well, I hope that that was some fun for you. It sure was for me. And I can't wait to see you tomorrow. Bye.